Okay, back and the next section, excuse me, where we left off was about the critical point where things become supercritical fluids, but that's actually, I think, better discussed at a point later. So we'll come back to that. And now we can go on to the next section, which is about sublimation and fusion. Remember, fusion is just a fancy word for melting. Sublimation is when you go directly from a solid to a gas, like dry ice does. And under this, looking at sublimation, and when you have molecules in a solid, they can vibrate in place because of thermal energy. That's true of molecules in liquids and gases too, but for solids, that's really the only freedom of movement, the ability to vibrate in place. There's still a distribution of energies though. Meaning that some molecules have more vibrational energy than others do. So some of the molecules will be vibrating faster than others do. And sometimes some of those molecules, particularly at the surface, will have enough energy to break free of their neighbors and enter the gas phase. And this is sublimation. Okay, so and they can do this without first going through the liquid. Okay, and that's usually because the current conditions will be unsuitable for the formation of the liquid. So if you're talking about, say, ice molecules that are vibrating in place inside your freezer, well, those ice molecules, if they have a lot of vibrational energy, they might be able to break free of their neighbors, and they can go into the phase of, the gas phase as water vapor, but they can't become liquid water because the freezer is below the freezing point. Or in the case of something like dry ice, some of the molecules will have enough kinetic energy to vibrate and sort of break themselves free of the attractions from their neighbors, but they go directly into the gas phase, not into the liquid phase, because liquid carbon dioxide cannot exist at normal atmospheric pressure. You need much higher pressure for that to happen. So, dry ice would melt into a liquid at pressures of, say, about 5 atmospheres or above. But at 1 atmosphere, it's going to go directly from the solid to the gas. And again, that's sublimation. Okay, sublimation is a change directly from a solid to a gas. It is endothermic. Some of the gaseous molecules can hit the surface and be recaptured by intermolecular forces. And so when these gas particles hit the surface of, say, the ice or the dry ice, they can be recaptured because they have lower kinetic energy and the intermolecular forces may be enough to hold on to them. And this process is known as deposition, which is essentially the opposite of sublimation. And deposition is exothermic. And it's because of sublimation that you can actually have the vapor pressure of a solid. So that seems at first glance like a silly concept, but actually it does have meaning. And so this is the pressure of a gas that's in dynamic equilibrium. With the solid form of the same substance. If ice is exposed to air, sublimation usually occurs at a greater rate. That is a greater rate compared to deposition. And that's simply because the newly vaporized water molecules will tend to move away from the block of ice, because now that they're a gas, they have a lot of freedom of movement. And once they move away, they can't be recaptured by the ice. And the result of this is shrinkage. And so again, I mentioned the other day that this is basically why your ice cubes shrink in the freezer. Even though you haven't been using them, and they certainly can't melt because the freezer is well below the freezing point of water, what they're doing is subliming. And again, the reason that liquid or water-based ice would sublime in a freezer is because the the temperature is below the freezing point of water, so it can't exist as a liquid. And the reason dry ice sublimes is because liquid carbon dioxide can't exist at 1 atmosphere. Okay, so that brings us to fusion. Fusion is melting again, and that's endothermic. You have to put energy in to accomplish that. As thermal energy is added, the temperature increases and the molecules vibrate faster. This is essentially the way we started out the last section on sublimation, except in fusion, we've got substances that are able to exist as liquids under the conditions, the present. So as thermal energy is added to a solid, that is, the temperature is increased. In other words, the only freedom of movement solids have is for the particles to vibrate in place. and greater thermal energy means more vibration. And as the molecules vibrate faster and faster, some of them will have enough kinetic energy to break free of at least some of the intermolecular forces, because again, there is a distribution of kinetic energies. Some of the particles will have more kinetic energy than others do. Some of them will have less. Some of those that have more than the others do will have enough energy to break free of the intermolecular forces and become a liquid. Okay. Remember though, when you're melting, when you're going from a solid to a liquid, you only have to overcome some of the intermolecular attractions between the particles, not all of them, because liquids still have fairly substantial intermolecular attractions between the particles. It's gases that have none. So to become a gas, you have to overcome all of the intermolecular attractions. Okay, and so the temperature at which that happens is the melting point. Of the substance. And the opposite process is known as freezing, or sometimes solidification, and that is exothermic. And remember, during any phase change, the temperature of the substance will remain the same because the energy is going into breaking down intermolecular attractions rather than raising the temperature of the substance. And it's only when all of the substance has undergone the phase change that the temperature can start rising again. Okay, the energetics, that is the energy changes, of melting and freezing. Well, first of all, it's just a reminder, melting is endothermic. That's essentially how ice does things like cooling drinks down. It's because when you put the ice in the drink, which is warmer than the ice, heat from the drink starts going into the ice in order to melt it. And that energy is expended in overcoming the intermolecular attractions among the H2O molecules in the ice. And so by the time the ice melts, a lot of that thermal energy has left the drink and it's colder. The energy required to melt 1 mole of basically a solid, any solid, substance, is the enthalpy or heat of fusion. Or delta H fuse, to distinguish from delta H which is the heat of vaporization. The heat of fusion of water is 6.02 kilojoules per mole. Notice, and that's for the process H2O solid going to H2O liquid. Notice the value of heat of fusion is quite a bit smaller than the heat of vaporization. And that is actually the case for all substances, although different substances will have different specific numbers. It's always true that the heat of vaporization is greater than the heat of fusion. And that's because in order to vaporize something from a liquid to a gas, you have to overcome all of the intermolecular attractions in the substance. In order to melt a substance from a solid to a liquid, you only have to overcome some of the intermolecular attractions. And so it takes a smaller amount of energy to overcome some of them than it does to overcome all of them. The opposite process is known as freezing, and therefore that would be exothermic. You remove energy in order to freeze something. And you can think of the heat of freezing as being just the negative of the heat of fusion. Or a negative 6.02 kilojoules per mole for water. Okay, so I'm going to say that the heat of vaporization is greater than the heat of fusion for just about all substances. I can't swear that there aren't any substances where the numbers are the other way around, but I'm not aware of any. And again, that's because to vaporize something to a gas, you have to overcome all of its intermolecular attractions. I'm going to go on to a new page for the next topic because it requires some space. And this is the heating curve for water. And it basically shows you the process of heating up a sample of H2O from ice well below its freezing point to steam well above its boiling point. And it shows you what happens sort of each step of the way. So if we look at a graph of the progress of this process, you know, we can plot temperature against heat added. And for a sample of water, we'll notice that if you take, say, ice at minus 25 degrees Celsius, and your goal is to heat it up to steam at 125 degrees Celsius, what you're going to see is the temperature will start rising for a little while, and then it levels off and doesn't rise for a while. And then it starts rising for a while again. Only the slope here, when it starts rising again, will be different from the original slope. And it rises for a while, and then it levels off again. When it levels off again, it levels off for a longer time than it did the first time. And then when it'll start heating up again, and again, the slope of the curve will be different from the first two times when it was at a diagonal angle like that. What you'll also find is that the temperature at this first plateau will be 0 degrees Celsius, the freezing point of water, or the melting point, depending on which direction you're going. The temperature of the second plateau will be 100 degrees Celsius, the boiling point of water. And that is not a coincidence because, in fact, that's what's happening at those 2 points. And what you've got here is 5 separate regions. If you're going to go all the way from, ice to steam, you're going to have basically 5 regions. Region number 1 will be the region where you're heating the ice. Region 2 will be the first plateau, and that will be where you're melting the ice. Region 3 will be once you've melted all that ice to liquid water, you then have to heat the liquid water up, to its boiling point. And so region 3 is heating liquid water. Then when the temperature levels off again, what you're doing is you're boiling the water. And then assuming that you're capturing the steam and continuing to heat that up, you can have a 5th region where you're heating the steam. And so that's the process. 5 regions, 2 of them are phase changes, and then 3 regions where you're heating each of the individual phases of matter. If you want to find out how much energy is involved in this process, first of all, you need to know how much water and what the atmospheric pressure is. So let's say we're doing this for 1 mole of water at atmospheric pressure of 1 atmosphere. And you'll need to calculate the amount of energy that enters the water during each of these phases. You're actually, anything going left to right, and because, heat added, if you're going left to right, presumably that means more heat added. And so that would be endothermic from left to right. And so you're adding energy as the water heats up, which makes sense. In order to calculate how much energy is going into the water, there are a couple different equations we'll need to use. First of all, there's energy that goes into the water within a phase, that is the slanted lines. So when you're heating up the ice, heating up the water, or heating up the steam, this equation applies to all of those regions. And Q is the symbol that we're going to use for heat in examples like this. And that's just going to be equal to MC delta T. M is the mass of the substance, H2O in this case, and that will be in grams. C is a constant for any given substance in a given phase. So water actually has a value of C for ice, and it has a different value for liquid water and a different value for steam. And what C is called the specific heat capacity. And it relates how much energy is required to change the temperature of 1 gram of a substance by 1 degree Celsius. And that will be a different number not only for every substance, but every phase of every substance. The units would be joules per gram degree Celsius. So the joules for each gram and each degree Celsius that the temperature is going to go up. And delta T is the change in temperature within that phase of the substance. Okay, that's for the slanted lines. For the horizontal lines, those are the phase changes. And remember, I mentioned that temperature doesn't change during phase changes. And that's why the lines are horizontal. This horizontal line means no change in temperature on this graph. And that number will be given by the delta H of the phase change, which would be heat of fusion or heat of vaporization, depending on which phase change it is, times the number of moles. In this case, that would be the number of moles of water. And that will give you Q during each of the phase changes. Okay, so what we can do is look at the amount of heat that has to be added to accomplish the temperature change, or to accomplish each of these 5 regions. Region 1, oh yeah, and I didn't mention that the final temperature is going to be 125. Region 1 is where we warm the ice up from -25 degrees Celsius to 0 degrees Celsius. So that's going to be MC delta T. The mass of the ice, well, we said it's 1 mole. One mole of water is 18 grams. C, for solid water or ice, is 2.09 joules per gram degrees Celsius. And that's a number that I would have to give you, or you'd have to look up. And delta T is the final temperature minus the initial temperature. In this case, that's 0 minus -25. And that's 25 degrees Celsius. And that ends up being 941 joules. Notice the energy is in units of joules because the specific heat capacity is in units of joules. Grams will cancel out with grams, and degrees Celsius will cancel out with degrees Celsius, leaving us with joules. 941 joules is also 0.941 kilojoules. You'll see why I did that in a moment. Region 2 is where we melt the ice. At the normal freezing point, which is 0 degrees Celsius. For that, we need the heat of fusion of water. Which is 6.07 kilojoules per mole. And Q for this step is going to be heat of fusion times number of moles. So it's 6.07, oh, sorry, 6.02 kilojoules per mole times 1 mole. Moles cancel, and we end up with kilojoules. And it's 6.02 kilojoules. That's why I changed this to kilojoules, because at the end of this process, when we add up all of the energies for all of the different segments, we need them to be in the same units. And it works out better if they're in kilojoules. You end up with a more reasonable number. Region 3 is where we warm up the liquid water from the freezing point to the boiling point. And that, again, is going to be MC delta T. Mass is, again, 18 grams because it's the same quantity of water. And the heat capacity for liquid water is 4.184 joules per gram degrees Celsius. And the change in temperature is going to be final temperature, which is 100, minus original temperature, which is 0, which is 100. And so when we work this all out, we get 7520 joules, which is 7.52 kilojoules. Region 4 is where we boil the water at 100 degrees Celsius. And that's another phase change. So what we have here is heat of vaporization times the number of moles. Heat of vaporization is 40.7 kilojoules per mole. And the number of moles is 1. So that's 40.7 kilojoules for that step. And let's see, there's only one more step to go, so I'm going to do that over here. Region 5, that's where we heat the steam. From 100 degrees Celsius to 125 degrees Celsius. That's a temperature change, so again, we're going to have to use Q equals MC delta T. C, the heat capacity of steam is, where is it? 2.01 joules per gram degrees Celsius. And the temperature change is 125 minus 100. That's 25 degrees Celsius. So MC delta T is 18 grams, again, because it's still the same sample of water. C is 2.01 joules per gram degrees Celsius. And delta T is 25 degrees Celsius. And when you multiply that out, we get 904 joules, or 0.904 kilojoules. And so what we were curious about, though, is what would be the amount of energy you'd have to add to go all the way from minus 25 to 125. which would be just the total of the energies for all 5 of these steps. And we had to divide it up into steps because each step involves a different substance with a different heat capacity or a different heat of vaporization or fusion. And so each step requires a different amount of energy, even in cases where the change in temperature might be the same, like it was between step 1 and step 5. You notice the amounts of energy. In each case, the temperature change was 25 degrees, and the amount of water was 18 grams in each case. But because the specific heat capacity of ice is a little bit different from that of steam, we ended up with somewhat different numbers for those 2 regions. And so the total energy would be just the sum of all of those numbers. 0.941 plus 6.02 plus 7.52 plus 40.7 plus 0.904 kilojoules comes to 56.1 kilojoules for the entire process, which doesn't really sound like a whole lot of energy, but this is the amount of energy for doing that with just 18 grams of water, which is only 18 milliliters, which is really not very much. So that's quite a bit of energy considering how little water is involved in this. Notice also that by far the step that requires the most energy is the boiling or the vaporization, 40.7 compared to the second biggest was 7.52. That's a big difference. And that's because when you vaporize something, you have to overcome all of the intermolecular attractions, and that requires a lot of energy. So that's not surprising. Yeah, that's basically the energetics of phase changes from the bottom right up to the top. We're past 30 minutes, so I'm going to end this segment now, and we'll be right back for the next.